Hi guys, welcome back to part 4 of heat transfer practice question, and today's topic is radiation. The first question we have is we have to find shape factor F21. So we have given two surfaces. The first surface is hemisphere and a flat surface, surface 2 is on its bottom part. So from summation law we know that F21 plus F22 is equal to 1, and we know that F22, because it is a flat surface, F22 would be 0. So from there we can calculate F21 is equal to 1. Next question is, a surface is at 7 degree that may be assumed to be black body in environment at 25 degrees Celsius. If 300 watt per meter square of radiation is incident on surface, we have to find radiosity in watt per meter square. So we have a body, black body, and the our G, which is incident on the surface, is 300, and we have to find out J, which is radiosity. So we know that for black body our alpha, that is absorptivity, is equal to 1 and reflectivity rho is equal to 0. So for radiosity we know J is equal to rho G plus EB, energy of black body. So for black body rho is 0 and EB we can calculate from sigma T to the power 4, and sigma we know that is Stefan-Boltzmann constant, 5.67 into 10 to the power minus 8. Temperature 1 and temperature 2 is given to us. Sorry, we have to calculate it for 7 degrees Celsius. So 273 is to convert it into Kelvin. So 7 degrees Celsius is given to us. So putting in the values of sigma and temperature, we get our J is equal to 348.5 watt per meter square. Next question is emission power E1 is given as 500 watt per meter square at temperature 1, and emission 2 is given as 1200 watt per meter square at temperature 2, and emissivity is given constant. So we have to find T1 is to T2. So we know that emission power is directly proportional to temperature to the power 4. So E1 by E2 would be equal to T1 by T2 to the power 4. So T1 by T2 would be taking the power to the other side and putting in the values of E1 by E2, we can get our T1 by T2 is equal to 0.803. Next question is, an enclosure consists of 4 surfaces, 1, 2, 3 and 4, and view factor of few surfaces are given. F11 is given as 0.1, F12 given as 0.5, F13 as 0.3, and surface area A1 1 meter square is given and A4 4 meter square is given. So we have to find F of 41. So we know that from summation law, F11 plus F12 plus F13 plus F14 is equal to 1, and in the question we are given F11, F12 and F13. All these values are given to us. So from here we can calculate our F14. Okay. Next, using reciprocity theorem, we know that F14 into area 1 would be equal to F41 into area 4. So F14 we have calculated, area 1 is given to us, and F41 we have to calculate, and area of 4 surface is also given to us. So we can easily calculate our F41 from here, which is equal to 0.025. Moving on to the next question, we have absorptivity alpha is equal to 0.4, emissive power is given as 5 watt per meter square, irradiation G is given as 6. We have to find radiosity. So we know that alpha plus rho plus Z is equal to 1. So from here we can say that our Z is not given to us in the question, so we would take it as 0. So we can say that rho is equal to 1 minus alpha. Okay, then we know that J, for radiosity, J is equal to rho G into energy of black body. So Rho is equal to 1 minus alpha. We have calculated it. Now putting it into this equation, we get J is equal to 1 minus alpha into G plus EB. So we are given with value of alpha, which is 0.4, and G is given to us as 6, and energy of black body emissive power is given as 5. So putting in all the values, we get J is equal to 8.6. Next question is, solid sphere 1 of radius r is placed inside a hollow closed hemisphere surface 2 of radius 4r. We have to find shape factor F21. So we have a hemisphere, and inside it there is a solid sphere. The radius of hemisphere is 4r, and the radius of sphere is r. 2r is the diameter, its diameter. So the sphere is called as surface 1 and the hemisphere is surface 2. So what we have to find out is F21, shape factor of radiation of the hemisphere on the solid sphere inscribed inside it. So we know that F12 plus F21 is equal to 1, and our F12 plus F22 is equal to 1, and we know that F22 would be 0. Okay, we have studied that for concave surfaces, and for flat surfaces the radiation on itself becomes 0. So from there we know that F12 comes out to be 1, and from reciprocity theorem we know F12 into area 1 is equal to F21 into area 2. Now in this equation, our F12 we know is 1, and we have to put the area 1 and area 2. So area 1 is for the sphere. So the area of sphere is 4 pi r square, because radius is given to us as r. And area 2 is for the hemisphere, the outer surface. Area 1 is for sphere, which is 4 pi r square, and area 2 is for hemisphere, and we know that the area of hemisphere is 2 pi into radius is given as 4r. 2 pi into 4r square plus pi into radius square. So putting in the values of area 1 and area 2, r would cancel out. So from there we can say that F21 comes out to be 1 by 12. Next question is, radiation heat exchanger is given, and very long concentric cylinders are there. Outer radius is r0 and inner is ri. We have to find radiation view factor of outer cylinder onto itself. So the outer surface would be a convex surface, so it would have some value. Like we know that for concave and flat surfaces the radiation on itself is equal to 1, and for convex surface, for flat and convex surfaces the radiation of body onto itself is 0, and for concave surface the radiation of body onto itself would be between 0 to 1. Please remember this point. So we have to find view factor of outer body into itself. So it is a concave surface on outside, so we have to find its radiation onto itself, and the inner radius is given as ri and outer radius is given as r0. So we know that F12 is equal to 0 radiation, because the surface is enclosed into a large surface. So we know that F12 would be equal to 0, and from reciprocity theorem F12 into area 1 would be equal to F21 into area 2. Now F21 would be area 1 by area 2 into F12. So we know that the cylinder is given, so area of cylinder is 2 pi rl. So putting in 2 pi ril by 2 pi r0 l into F12. F12 is 1, so F21 comes out to be ri by r naught, inner radius by outer radius. So from summation law, we know that f12 plus f22 is equal to 1. So f22 would be 1 minus f of 21, which would be 1 minus ri by r naught. Next question is, two surface of area 1 is given as 300 meter square and area 2 is 150 meter square. We have to find nature of surface 1 when area 2 is enclosed by area 1. So the surface could be of any shape. It could be a flat surface or a concave surface or convex. It could be of any shape, the outer and inner surfaces. So we have to find uh, nature, like in what shape the outer surface or the inner surface is. We have to find the nature of the surface. So how can we find that? We know that radiation of a body onto itself is zero when it is flat or convex surface, and it would come out to be between 1 to 0 if it is a concave surface. So if we find the radiation of body of surface 1 onto itself, then we can easily know the nature of the surface. So let's get started. So we know that f21 would be equal to 0 because the second surface is enclosed within first surface. So f21 would be 0, and from summation law we know that f21 plus f22 is equal to 1. So from there we can say that f22 comes out to be 0. Now that f22 has come out to be 0, like area 2 is enclosed within area 1, so the it is 0. So the inner surface would either be convex or flat surface. Okay, now moving on to, we know that f21 into area 2 is equal to f12 into area 1, reciprocity theorem. Okay, so f12 would be area 2 by area 1 into f21. f21 is 1. Okay, area 2 is given to us, area 1 is given to us, so f21 comes out to be 0.5. Now putting it into summation law, f11 plus f12 is equal to 1. From here f11 comes out to be 0.5, and this value of f11 is between 0 to 1, which indicates that the outer surface is concave surface. One more thing, in the previous question we have taken area as 2 pi rl because this is open-ended cylinder, like because it is heat exchanger, so flow is taking through the cylinder, and which is why the area of the cylinder is taken as 2 pi rl, because we know that for closed surface cylinder the area is 2 pi rl plus the area of top surface and bottom surface, which is 2 pi r square. So in this case this is an open cylinder, which is why the area is 2 pi rl. So moving on to the next question. Next question is, hot water tank of diameter 0.5 meter and its height is given as 1, ambient temperature 25 degrees Celsius, tank surface is oxidized copper, and its emissivity is given as 0.8, and its peak temperature is given as 80 degrees Celsius. So we have to calculate heat loss by radiation. So we know that Q12 is equal to sigma Boltzmann constant into T1 to the power 4 minus T2 to the power 4 into area 1 into our emissivity. So it is given that the cylinder is enclosed within a large space and its radius and height is given to us. So to calculate the area of cylinder, closed cylinder, so the area is 2 pi rl plus 2 pi r square, and it comes out to be 1.963 meter square. And Q1, to calculate Q12 we are going to put value of sigma, which is Stephen Boltzmann constant, and temperature 1 80 degrees Celsius, temperature 2 25 degrees Celsius, area we have calculated and emissivity is given to us as 0.8. So putting in the values, Q12 comes out to be 680 watt. Then the next question, two plates are given to us. Temperature 1 is given as 100 Kelvin, temperature 2 is 40 Kelvin, and the distance between the plate is 10 millimeter, and our emissivity for plate 1 is 0.5 and for plate 2 is 0.25, and we have to calculate heat transfer taking place between the plates. So we know that Q by A, heat transfer per area heat transfer by area is delta E by summation of R, where E is our energy emitted. So which is equal to delta E is equal to sigma T1 to the power 4 minus T2 to the power 4, and we have to calculate some summation of the resistances. So let's draw a network diagram for this. So we know that surface resistance is given as 1 minus E1 upon E1 minus, sorry, we don't call it E1, epsilon 1. So 1 minus epsilon 1 upon epsilon 1 minus A1. This is the surface resistance of first plate. Then we have space resistance. Space resistance is calculated as 1 by F12 into area 1. Then again the surface resistance of plate 2, which is 1 minus epsilon 1 upon epsilon 2 minus area 2. So we have to calculate Q with respect to area. So in the equation, our equation would come out to be the value of sigma. We have put temperature 1 to the power 4 minus temperature 2 to the power 4 upon 1 minus epsilon 1 upon epsilon 1. Area is not given to us, so we have taken area as 1 plus 1, because F12 is equal to 1 because this is a long plate, so which is why F12 is taken as 1. Then 1 minus epsilon 2 upon epsilon 2, again area is taken as 1. So solving the all the values, we get our Q by A is equal to 1.1049 watt per meter square. Next question is, peak wavelength of radiation emitted by black body at temperature 200 Kelvin is 1.45 μm. Wavelength is given at temperature 200 degrees Celsius. So now we have to calculate temperature if the peak wavelength changes to 2.90. So from Wein's displacement, we know that our wavelength is inversely proportional to temperature. So we can say that lambda 1 by lambda 2 would be T2 by T1. Now putting in the values of lambda 1 and lambda 2 and temperature 1, we can calculate the temperature 2, which comes out to be 100 Kelvin. Next question is, two infinite plates are there and the heat transfer is decreased by 80%. So we have to find number of shields required to be placed between them. So basically they are asking that we have two plates, and now initially there were two plates and the heat transfer is decreased by 80%. So we have to calculate like how many numbers of plates should be there so that the heat transfer would come down to 80%. So for 80% heat transfer reduction, initially heat transfer was full heat transfer was taking place, so it was 100%. Now it has reduced to 80%. So due to 80% heat transfer, Q after shielding would become 0.2 times of initial heat transfer. So we know that Q with shielding upon Q without shielding is equal to 1 by n plus 1, where n is number of shields. So now that the heat transfer is reduced by 80%, so the final heat transfer with shielding would be 0.2 times of initial heat transfer, which is Q. It is equal to 1 by n plus 1, and we have to find number of shields. So solving this, we get n is equal to 4. So if we would put 4 plates between the two shields, two infinite plates, if we put 4 shields, then we would our heat transfer would reduce 80%. Next question is, two large parallel plates is at a gap of T1 1500 kelvins and T2 is given as 500 kelvin, and these are two parallel large plates. Epsilon 1 is given as 0.5, epsilon 2 is given as 0.2. The emissivity of plates are given, and it is also Stephen Boltzmann constant is also mentioned in the question. So we have to find heat transfer between the plates in kilowatt per meter square. So we need to know that to calculate heat transfer, the formula is Q by A is equal to delta E by summation of R. Delta E for energy emitted for any body is equal to sigma Stephen Boltzmann constant into T1 to the power 4 minus T2 to the power 4 upon summation of radiation. So for this diagram we are going to make our resistance network. So for surface 1 we have surface resistance as 1 minus epsilon 1 by epsilon 1 into area, and for the space, then surface resistance of surface 1, space resistance, then resistance of surface 2. So space resistance is 1 by f12 into area, and then surface resistance for surface 2 would be 1 minus epsilon 2 by epsilon 2 into area. So in this formula, putting in the values which we are given, so Q by A would be sigma 5.67 into 10 to the power minus 8, value of sigma, into T1 which is 1500 to the power 4 minus T2 500 to the power 4 upon 1 minus epsilon 1 given as 0.5 upon epsilon 1. Area is not given, so again we are going to take area as 1 because area is not given, and then F12 would be 1. Why? Because these are two large plates. So F12 would be 1 because we have studied that for two large plates, the radiation for plate 1 would fall, all the radiation from plate 1 would fall on plate 2. So F12 would be 1. So plus 1 minus epsilon 2 which is 0.2 by epsilon 2 0.2. So Q by A, which is our heat transfer between the plates, come out to be 56.7 kilowatt per meter square. Next question is, temperature of a solid surface is increased from 310 Kelvin to 1000 Kelvin. So initial temperature was 310 Kelvin and the final temperature is 1000 Kelvin. Temperature is being increased. So we have to find emissive power, our E. So for that we know E is directly proportional to temperature to the power 4, because we know that E is equal to Stephen Boltzmann constant into T1 to the power 4 minus T2 to the power 4, and it can be written as E is directly proportional to T to the power 4. So from there we know that E2 by E1 would be T2 by T1 to the power 4. Okay, so putting in the E2 would be T2 given as 1000 Kelvin by T1 as 310 Kelvin to the power 4 times of E1. So E2 comes out to be 108 times of E1. Next question is, heat loss percentage we have to calculate if one shield is added and if two shields are added of same emissivity. Like we are giving two plates, we have to calculate heat loss. Like initially there was some heat transfer, like heat transfer is taking place. Now we have added one plate and we have to calculate the reduction in heat transfer, and after that for the same emissivity two shields are added, so we have to calculate heat transfer reduction in that case. So when one shield is added, we know that Q of shield is equal to 1 by n plus 1 into Q without the shield. So n is number of shields, so Q shield by Q would be 1 by n plus 1. N is 1 plus 1 2, that is 0.5. So 50% reduction of heat transfer takes place when one shield is added between two plates. Then now we are adding two shields. So Q shield by Q without shield would be 1 by 2 plus 1. 2 plus 1 is equal to 1 by 3. So this means there is 33% reduction in heat transfer when we add two shields between two parallel plates. Next question is, we have to find percentage reduction in net heat transfer. So we are given two plates, temperature 1 of plate 1, T1 and at T1 and T2 temperature, and our epsilon 1 and epsilon 2 of both the plates are same, being zero point 0.6 and zero point 0.6, and two shields are added between these plates. So epsilon for shield 1 is 0.05 and epsilon for shield 2 is also 0.05. 0.05. Okay, so we know that Q shield upon Q without shield is equal to 1 by n plus 2. Sorry, 1 by n plus 1, and n is number of shield given as 2. So Q shield by Q without shield comes out to be 1 by 3. Okay, now we know that F12 is equal to 1 because these are two large plates. So in that case, F12 comes out to be 1. So we have to first we would calculate Q without heat transfer without the shield. So in case of Q without the shield, we know that it would be delta E by summation of R when there are no shield. So in that case, only the plates would be present. So for plates, like for Q without shield, we have only plates at T1 and T2 temperature, and epsilon 1 being 0.6 and epsilon 2 being 0.6. So in this case, the summation of resistance would be resistance of surface 1 plus resistance of space resistance between the plates and resistance of plate 2. So it would be 1 minus epsilon 1 by epsilon 1 plus the space resistance, which would be 1 by F12 into F12 into area 1. Area is not given, so we are taking area as 1 plus resistance of second plate, which is 1 minus epsilon 2 by epsilon 2. So putting in the values, we get Q without our shielding with respect to area. Sorry, Q without shielding we get is 0.428 into, we don't know the value of sigma and temperature, so we are going to take it as it is, sigma into T1 to the power 4 minus T2 to the power 4. So now we have calculated Q without shield. Now we are going to calculate Q with shield. So in this case, epsilon 1 is given to us, epsilon 1 and epsilon 2 being 0.6, and the epsilon of shields are also given as are equal and given as 0.05. So we know that Q with shield, the formula given to us is delta E, which is sigma into T1 to the power 4 minus T2 to the power 4 upon 1 by epsilon 1 plus 1 by epsilon 2 plus n number of shields into 1 by epsilon of sheet 1 plus 1 by epsilon of sheet 2 minus n plus 1. This is Q of shield, formula for that. So we don't know the numerator value, so we are going to take it keep it as it is, and for denominator we know that value of epsilon 1 and epsilon 2, which is 0.6, and we know that shields epsilon of both the sheets, which is 0.05. So putting in those value, and number of shields are 2, so putting in those value, we get our Q shield is 0.0124 into sigma numerator, which is sigma into T1 to the power 4 minus T2 to the power 4. So percentage reduction in heat transfer would be Q without the shield. Before adding the shields, our Q, which we have calculated, then Q with the shields upon Q without the shields into 100. So this sigma into T1 to the power 4 minus T2 to the power 4 would cancel out, and Q without 0.426 minus Q with shield 0.124 upon Q without 0.426, it comes out to be 97.1%. Then our next question, which is our last question for radiation, is we are given three surfaces. These are the surfaces are, this is first surface, this is our second surface, and this is our third surface. And I would just zoom it for you guys. Temperature 1 for surface 1 is given as 60 Kelvin, area is given as 6 meter. Temperature 2 of surface 2 is given as 80 Kelvin and area is given as 5 meter. And temperature 3 is given as 30 Kelvin. And we are given that f of 1, 2 is given as 0.5, and Stephen Boltzmann constant we know, also given in question. So we have to find heat transfer from surface 2 to 3. Like, what is the heat transfer from surface 2 to 3, which is Q of 2, 3 and F of 2, 3, shape factor for 2, 3 as well. So, okay, now we know that these are flat surfaces because it is given that these are flat surfaces. So F11, F22 and F33 would be 0. Radiation on the body itself for flat surface is 0. Okay, from reciprocity theorem we know that F12 into area 1 would be equal to F21 into area 2. So F21 would come out to be F12 into area 1 by area 2. So we know that F12 is equal to 0.5 given to us. Area 1 is given as 6 meter. Area 2 is given as 5 meter. So putting in the values, we get F21 is equal to 0.6. So we have also drawn a resistor network diagram. So I will zoom in it a bit. So our three surfaces, this is surface 1, surface 2 and surface 3. So as we can see from the diagram, surface 1, surface 2 and surface 3, they in between them they have space resistance. So from surface 1 to surface 2 there is some space resistance acting on, and from surface 2 to 3 there is some space resistance acting between them, and from 1 to 3 as well space resistance is acting between them. So we have drawn a circuit diagram for that purpose. So temperature 1 of surface 1 is 60 Kelvin, temperature 2 of surface 2 is 80 Kelvin, temperature 3 of surface 3 is 30 Kelvin. So the space resistance between surface 1 and 3 would be 1 by F13 into area 1, and between surface 1 and 2 space resistance would be 1 by F12 into area 2, and between surface 2 and 3 space resistance would be 1 by F23 into area 2. Okay, and from summation law we know that F21 plus F22 plus F23 is equal to 1. Okay, and because these are flat surfaces, F22 is 0. Okay, and we have calculated F21, which is 0.6. Putting in the value of F21 we can easily find out F23, which is equal to 0.4. So we had to calculate F23. Done with that. Next we have to calculate Q23. So we know the formula of to find out heat transfer is sigma into T1 to the power 4 minus T2 to the power 4 by the summation of resistances. So from this resistance diagram, we know that the resistance between surface 2 and 3 is the space resistance between surface 2 and 3 is 1 by F23 into A2. Okay, so the temperature difference between surface temperature T2 is given as wait a minute, temperature difference between surface 2 and 3, this would be 80. T2 is given as 80 Kelvin and T3 is given as 30 Kelvin. So Q23 would be sigma into the temperature of second surface minus temperature of third surface, both to the power 4, difference between them, upon resistance, which is the space resistance between surface 2 and 3, which is 1 by F23 into A2. So putting in the values, sigma we know, Stephen Boltzmann constant, into temperature, second surface temperature 80 Kelvin to the power 4 minus 30 Kelvin to the power 4 upon area is not given to us, so we are going to take area as 1 upon F23. Sorry, area is given to us. Area is 5 mm. Sorry, area is given to us 5 mm, and F23 we have calculated as 0.4. So I would once again repeat it for you guys. We had 3 surfaces, 1, 2, 3, and between these there is some space resistance taking place. So we would draw our resistance network diagram for these. So these are our resistance diagram for this is surface 1, surface 2 and surface 3. So we have to calculate heat transfer between surface 2 and surface 3. So between these surfaces there is space resistance, and space resistance we know is 1 by F of 2, 3 into area of 2. So to calculate Q, we have used the formula Q is equal to sigma into T of second surface to the power 4 minus T of third surface to the power 4 upon resistance between them. So we know that resistance between them is F of 2, 3 into area 2. So putting in the values, we can calculate our Q of 2, 3.